So we've got these 3 problems that we should hopefully know how to do. With Bowers, we will always kind of, at the very least, talk through them. I will usually work them through up here. I may hand the iPad to you guys at some point to do them, but again, I am tired and I am sitting. So I will do them today. What do we do for this first one? How do we evaluate the expression when we're told really random things here? That our A is 6, our B is -3, and our C is -1. What do we do with those? Substitute them in. So every place that has an A gets a 6, every place that has a B gets a -3, and every place that has a C gets a -1. So I can rewrite this as, instead of saying B squared minus 4AC, we're going to have our -3 go in place of that B squared minus 4 times the A, which is 6, times the C, which is -1. Whenever I do substitutions like this, I always want to put them in parentheses. It really helps us remember the fact that we are multiplying by -1 and not subtracting 1. Hey, hey. I'll take that. Thank you. Watch out. Gotcha. Sweet. Marked. So I always substitute them inside parentheses like this. It's a good habit to have. It also helps remind us of some notation things, like especially when we're doing this piece, it's really helpful. So as we're coming through this to try and simplify, what are we going to do first? What's our first step going to be? I was going to say, PEMDAS is our, kind of the goal, right? So we typically want to do our parentheses first. There's nothing inside my parentheses, and we can't see that on the document. There's nothing inside my parentheses I can simplify. So what's the next thing we can do? Exponents. So I can take my -3 and square it. What is -3 squared? Be careful. I've heard both 9 and -9. What do we think? Because what does it mean to be squared?
Multiply by itself.
By itself. So -3 times -3. A negative times a negative is positive. Okay? So if you especially are to type this in a calculator, which honestly would be impressive, I don't have them out right now. But if you were to type this in a calculator and you didn't put parentheses around the -3, it would tell you -9. 100%. Because calculators are really bad at trying to figure out what we actually want. So this is actually going to be a +9. -3 times -3 is a +9. And then we have our minus over here. And we can do these in the same kind of step. We don't have to do them as separate steps. But the next pieces in our PEMDAS, we do our multiplication or division in the same step. So we can do our multiplication here of our 4 times 6 times -1. What is 4 times 6 times -1? Yeah, -24. So this was all 3 of these multiplied together. You can do it in pieces. You can do it in one big chunk like that. We can take and do it in whatever order we want. Just like it doesn't matter if you do 2 times 3 or 3 times 2. It doesn't matter what order we do them in. We can multiply these pieces in the one chunk in whatever order I want. So we can do that. What happens when I have minus a negative number? What does 2 minus signs do to get together? It makes it positive. They undo each other. They are opposites. So this is actually the same thing as 9 plus 24. And what is 9 plus 24? 33. So our final answer here is 33. I don't like having it there because that looks weird. So we're going to put it here. And I know it's going to be a little small, but that's where it is. I will badly dance whenever music plays on purpose. Just wait till we bust out the I have been known to bust out the sprinkler. So if I hear it from your headphones, I will just stand in front of you and just it kills a song so fast. So, just saying. I have no shame. All right. So that's how we do that first one, just kind of substituting pieces in. We will see this expression, the b squared minus 4ac, a gabillion and a half times. Not even kidding. A gabillion and a half times. It is a very common phrase. We're going to use it, especially when we get into chapter 3, a lot. Like, it's a thing, so it's helping us get ready for something. So we will see that particular mathematical phrase a bunch of times. Let's look at number 2. What can we do for number 2? Be more specific. Combining like terms, yes, but how? Yeah, let's subtract the 8x from both sides. I want to get those x's together. I really don't like having to deal with them together, or on opposite sides of the equal sign. Gross. So let's get them at least together so we can see what's going on there. So if I subtract 8x from this side, those go away. Awesome, that's what I wanted. I'm left with a 7. But what happens on the right side too? Same thing. Oh, now I have no more x's. I just get that 7 equals 7. So what does that mean my solution is here? Or how many solutions do we have? An infinite number. I can use any x I can think of in the world. I can use an x of 2. I can use an x of 12. I can use an x of 547,842.8. And this will still be true. It doesn't matter what I use. Everything works. So my solution here is all real numbers. I did show you guys that shortcut for writing all real numbers on Friday, which was when we do a capital R with an extra stick. Means the same thing. The other way you'll often see this written is that we have an infinite number of solutions, so we can just write infinity, which is a sideways 8. So all 3 of these would be 100% totally valid answers. 100%. Okay. One more. Toot toot. What can we do for number 3 over here? And I can see 2 different ways to approach this. So I'm going to do a little barrier right here. You don't have to write down both ways, but I'm going to show you both ways. Well, what did you do to try and solve this? Distribute the 5. That is absolutely a valid way to do it. If I'm going to take and distribute that 5, that's going to give me 5c minus 5 times 6. Well, 5 times 6 is 30 equals 25. Don't like that overlapping. There we go. Oh, I'm going to have to go talk to the 8th graders if they keep doing that. What would we do next? I was going to say, careful, we're not want to subtract 30. We want to add 30 because of that minus sign. So we add 30 to both sides. Gorgeous. So we get 5c equals 55. So what's c going to be? 11, because we divide both sides by 5. So c equals 11 divided by 5. That is 100% a valid way to go through this. Did anybody do anything different in the very, very, very first step? You can divide by 5 on both sides. It's not better. It's not worse. It's just different. So if I divide both sides by 5, then we can get c minus 6 all by itself. And the right-hand side is 5. So you can divide both sides by 5 here, and that's a totally valid way to do it. Then what do we do next? Add 6. Yeah, exactly right. We add 6. We add 6. And that gives us C equals 11. We get the exact same answer, which is kind of cool. Two totally different processes. We had totally different numbers. And as we get further and further into mathematics and as we grow as mathematicians, that's going to happen more and more. We have more than one pathway through it. There is not one, you must walk in these footsteps to get to the answer to get there. There are lots of options. There are lots of different pathways through problems. So part of what we're going to be doing in this class is discovering which pathway to get there. So I like to think of these two different pathways as paths around a tree. I can go to the right, I can go to the left. It doesn't matter. I still got around the dang tree that was in my way. So it doesn't matter which path we take. That is part of the reason you guys show me work, so I know what pathway you went. Because I am not psychic. As hard as I try. Okay, questions on these three? Cool. So you just hang on to that paper and you'll turn it in on Friday. Huzzah. Grab out your notes packet. We are going to look at those same graphs we looked at on Friday. So we're looking at these guys because we need to finish and look at that interval notation that we didn't really talk about. And then we're going to finish out to page 3 today. So you should have at least this much information on that graph on page 2. Yes, dear. Yeah. Does anybody need a copy of the notes packet? All right. So before we just straight up hop into this graph, I'm going to look at those, the inequality of the number line things that you don't have to put up here. We just kind of use them to talk about and remember our inequalities. So I'm going to talk about our interval notation. This was our algebraic notation when we have our less than, greater than, that kind of stuff. And our interval notation is going to be conveying the same information, just in a different way. And it's a way that's used a lot in continuing mathematics. It's going to be the way I tend to write, but I just wanted to make sure we, had a chance for that. So when we're writing interval notation, what we're going to do is we're going to have basically 2 blanks where we're going to put the smallest it can be and the biggest it can be. And we'll usually have them inside parentheses. So if we think about this number line over here, how we have our x has to be less than 2. The smallest it can be is as small as I can imagine. It can go off the edge of the page here. I can have 1, 0, negative 1, negative 4, negative 10, negative 500, negative 5 million, negative 5 billion. Keep going on and on and on, out for forever. So the way we say that is we can go out to infinity, but since we're looking at negative numbers, we're going negative infinity. So the smallest this can be is negative infinity, but the biggest this can be is right here at 2. It's the same number we used for the algebraic, for our inequality over here. On our lower one down here, same kind of vibe. We're going to have 2 spaces that we think about. You don't have to draw the lines. It's just so that, we can think about it. On this one, what we have is that instead of 2 being our biggest number, 2 is our smallest number. So our smallest number is 2, but this goes all the way up to bigger and bigger and bigger, as far as we can imagine, 10, 20, 500, 5 million, 5 billion, all the way out to infinity. Ooh. Can't go beyond Buzz Lightyear's wrong. Whenever we have an infinity, we are going to use a parentheses, for sure, just like we did up here. But because we had this less than versus our greater than here, the only difference is when we have the greater than equals to, we use a very squared off parentheses. It's called a square bracket. What this tells me is I can touch the 2. I'm allowed to touch the 2. I can stand on it. I can poke it. It's right there. I can touch it. On this guy, no, I know you get grumpy when I play touchscreen games. On this one, remember this was a hole, that's a lava pit. Somebody poked a hole in our road and I gotta jump over it. Like a pothole or a lava pit. I can't touch it. So that's what the parentheses are. The parentheses are like an obnoxious little sibling going, I'm not touching you, I'm not touching you. So I can't touch this too because it's got the open hole there. But I can touch this too because it's closed. That's what they mean. Now, I am not going to be super petty about our brackets. There are some things I will be petty about and it's super duper important. The brackets, I am not as petty about it. When you get into pre-cal, they're used a lot and we are very, very petty about them. Like, it's super important. But as we're just starting to kind of get our feet underneath us with this interval notation, I'm not going to be super petty about it. I will always try and communicate when there is something that is very, very meticulously important versus something that we're going for the vibes. We're going for the vibes of our interval notation as opposed to the I am aggressively petty about it. So that's kind of the vibe. We are going to take those same graphs we worked with on Friday and we did our algebraic notation. We are now going to do our interval notation on these. Okay, so I have those same graphs from page 2 where we're going to practice this. So we had our domain of all real numbers here. That means our x's, we could go anything on either side. I could pick an x of 0 and find a value. I could find an x of -2 and find a value. I could go out to the x of -400,843.8 and I could find a value. It's just going to be in space at this point. But I could do it. This thing totally works everywhere. So the way we write our interval when our answer is all real numbers is I can go from -infinity all the way to the left as far as I can imagine out into the existence of the universe, up to as big as I can imagine, positive infinity. So that is the same thing as saying all real numbers with a funky looking R. I can use anything. X can be whatever the heck I want. No rules, no regulations. Chaos bounds. With our range here, that's where it's getting a little more specific. This one says our y has to be bigger than -3, meaning if we look at our y values here for our range, our very, very smallest, I can't go lower than, our very, very lowest point is this -3. I can't get beyond down to -4. The very, very lowest is -3. So our interval for our range has this -3. That was backwards and kind of impressive. Holy cow. My brain went broken there for a second. So we have our -3 as our lowest point. What's our highest point on our range? Infinity. That's as high as it can possibly go. It goes up, 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 up forever. So infinity always gets a parenthesis every single time because infinity is an idea. I cannot touch it. But this -3, I can touch it. Boop, right there. I'm touching it. Blah, 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 blah. It's right there. I have a point there, so I can write it there. Boop. So it's very, very similar. They're very related. These two things mean exactly the same thing. You don't have to have the little line there. It's just me trying to talk about we're filling in this space here. Okay? So this is what it looks like to write them in our algebraic notation versus interval, algebraic and interval, okay? Let's do the squiggly one. We did that one too. Cool. So again, this one was really close. We had this, and then we had to jump over our lava pit here, and then we could keep going. And we saw our algebraic notation being that we could either have this way, where I say, all right, it's everything except -2, or I can write it as two separate pieces. When we're doing it in interval notation, we're going to think about it more as two separate pieces, that my x has to be either smaller than -2 or bigger than -2, because it cannot be -2. So this is kind of the shortest way to write it, is that x can't be -2. Like, it's valid. This is going to help us more with our interval notation, because interval is always going to be a true region, like it's including. It is always the things that work. So by writing things that don't work, it means I can't take that and like translate it into interval notation. So when we are writing our intervals here and we have something in the middle causing a problem, think about it as two separate pieces. So think about these guys as two separate pieces for our domain here. So if x is less than -2, that's our purple piece here, the way we put that as an interval, the smallest that purple piece can be is -infinity. It goes on and on and on forever. Yeah, it's look like it's going real far up, but it's still going out. It's just going out real slowly. So it is going out. So this goes out to -infinity, and this purple piece, if we just look at that guy, it goes up to maximum of -2. And since we cannot be -2, I can't touch -2, it is a pit of lava, I gotta jump over, we put a parenthesis. For the green one, it's very, very similar because the green piece is where my x's have to be bigger than -2. So the smallest that green chunk can be is -2. And again, I cannot touch it. So I put my parentheses. And the biggest that green piece can go, it's a little easier to see because we had a lot longer piece of the green section. Is it still continuing outwards? It's going on and on and on forever. It can go all the way up to infinity. It just takes it a minute to get there. Traditionally, when we do two different intervals like this, and if you get to pre-cal, you'll see this, you're going to join in with a U. We're not actually going to talk about what that U means until we get to like chapter 10, so I'm not super petty about it. If you want to put a U, if you want to put an and, if you just want to leave it blank and just have them smashed next to each other, again, not something I'm going to be petty about. Traditional effectively communicates it, and a blank also works for me. Like, again, not going to be petty. Let's do our range on this one. We already said that our range was going to be all real numbers, and we've actually done all real numbers as an interval. So our all real numbers as an interval, that's when it means I can have absolutely anything from the smallest number I can possibly imagine, so our -infinity, up to the biggest number I can possibly imagine, positive infinity. Okay. Questions on those two? Because I know those are the two that we did on Friday. We didn't quite get to the dot one on Friday. But we're going to go ahead and grab the dot one now. It just lets us kind of wrap those up, and then we'll talk about those last words. All right, so this third graph here, this is at the top of page 3. We don't have any lines here at all. We're going to talk about what this kind of graph is called in a minute. And honestly, they have the same notation, whether it's algebraic or interval, no matter what. And the way we do this is if we think about all of these points as ordered pairs, like if I was to write their address, like this guy is -3, 1.5. And this guy is -2, -1. So like these addresses are 1, 1. For our domain, remember has everything to do with our x values. So we just straight up list the x values. So our domain has everything to do with the x's. So when we're writing out either our algebraic notation or our interval notation, we just straight up list them. Tradition has us go from smallest to biggest. Again, I am not going to be super petty about it, but we're going to list our x values. So the smallest x value we have on this graph, I'm going to read it because I can see it. There we go. We have -3 is my smallest x value. That's this guy. Then my next smallest x value is this one, the -2. And then we have our -1. And then my next smallest piece is this 0. So we just list them out. And then we'll have our 1 coming from this guy. And then our 1.5, which you can write as a decimal, you can write it as a fraction, mixed number. I don't really care. You're getting the point across. And 2 is our biggest x value. A lot of times when you're looking in the answer key or things like that, it will have these squiggly brackets in here. This just means it's the set of these numbers. I'm, again, not going to be super petty about the squiggly brackets. I know they're a pain in the butt to draw sometimes. If you do that, I totally count that as a squiggly bracket. Okay? It's kind of like a half of a heart and then another half of a heart coming up from the bottom if you really want the pretty ones. But if you just scribble, I get it. 100%. And it is 100% the exact same thing for interval notation. So whenever we have just dots, it's just a list, no matter what type we want to write. And since our domain has everything to do with our x values, our range has everything to do with our y values. And it is 100% the same thing. We are just making a list of our y values, typically in smallest to biggest order. I will not be petty about it, but it's just the way we typically do it. Makes my brain itch if I don't, so I always do mine from smallest to biggest. And again, I'm just going to put my squiggly bracket, and I'm going to make my list. Our smallest y value that we have, this guy down here, -1 is my smallest y value. Then we have our -1/2. This guy is our next smallest y value, -1/2. Or -0.5, genuinely don't care. Our next smallest y value is this guy, or 0. Then our next smallest y value is this guy, our 1. And then our 1.5. And then our 3. And then our 4. So it doesn't matter what kind of notation we're writing when I have separate points like this, separate dots. We just make a list. Domain means list the x's. Range means list the y's. Let's remember our words from Friday that we have down here at the bottom, our function and our one-to-one function. So use our very fancy schmancy high-tech math tool known as the stick for these two tests. And we want to test and see if something's a function. Which way do I hold my stick for if it's a function? Do I do a vertical or do I horizontal? I don't remember. Think about Friday. The first test we always do, because it got to be a function first. Vertical line test. That's when we do the vertical one. So that one happens first. Vertical line test is first. It's got to be a function first. So we want to see, does it ever touch more than one dot at the same time when I go across? Did I ever touch more than one dot at the same time? No. We don't have more than one. So this is a function. If we ever cross more than one dot at the same time, we're not a function. We should almost always have functions in here. So since we did vertical for is it a function, to do our one-to-one function, that's when we go on guard. One-to-one function. So now I want to know, do I ever touch more than one dot going this way at the same time?
No.
No. So this passes our horizontal line test. So this one is also a one-to-one function. So in order to be a one-to-one function, for us to do this one, it has to first be a function. So function, then one-to-one function. If it fails this, it's not one-to-one because it's not a function. Okay, so now we're going to look at 3 words, and then we're going to come back and look at these exact same 3 graphs to give them the words, and then we're done. Okay? So 3 words. Continuous, discontinuous, and discrete. So continuous, I feel like we can kind of guess that one a little bit. If we think about a continuous journey, if you're grown-ups say we are going on a continuous journey, that means we are not stopping ever. No jumps, no breaks, Nothing else. Nothing weird. It goes from one end to the other. Nothing in the middle. So a continuous function is a function with no breaks, jumps, or holes in the middle. So that doesn't mean it has to go on forever. Like, it doesn't have to have arrows on both ends. It's okay if it stops, has a smooth line, and then stops again. That's totally okay. It doesn't have to have closed points or open points anywhere. It just can't have any holes in the middle, no lava pits. It cannot have where it jumps from one line to another one. Nothing else. It is smooth in the middle. So it would be something like this. Or you could have an arrow on it. That's fine. It's nice and smooth. No jumps, no breaks, no squiggle, or no craziness happening. Might be squiggly, might look like a roller coaster, but it's not going to jump the track. I'm going to jump down. Oh, yeah, no, we'll do discontinuous next. Let's look at discontinuous. So if we think about continuous and then discontinuous, think about that prefix. Dis means not. So if it is not continuous, it would be something that does have holes or breaks or jumps in the middle. So this will be a function that has at least one hole or break or jump. And then there's a very special kind of discontinuous function called a discrete function. It is discontinuous, but it is a very, very specific one. And it's one that we have seen very, very recently, because what a discrete function is a function where no points are connected. They are separate dots. So they look a lot like a scatter plot, this kind of vibe. All right, I've seen one like that recently. Oh my gosh. So none of the points are connected. It's just dots. So if we have a very, very smooth line, we have a continuous. If we have just dots, we are discrete. If it is anything in between, it is discontinuous. Okay, so we're going to look at those three graphs we just looked at, and we are going to decide if they are continuous, discontinuous, or discrete, and that is it. So you guys have all three down there at the bottom. I'm actually going to flip back to the ones that have all of our information on it so we can look at them, but you can look at whichever ones you want. It's the same ones that you guys have down here, and if you want to put it here, that's totally valid. I just was taking it back to the information pages because it lets us see it again. So let's look at this first one, the U-looking one. What do we think? Is this continuous, discontinuous, or discrete? Continuous. The way you can kind of test that is if I can trace it from one end to the other and I don't have to pick up my pen, it is continuous. So this one is, I'm getting a chunkier pen. There we go. Continuous. So then look at this kind of S-shaped one. What do we think about this one? Discontinuous. So this one is not continuous because as I trace it, I have to jump over the lava pit. I have to jump over that hole. But I do have things that are connected up. So I have lines here, which is why it's not discrete. If you have any lines, it is not discrete. Discrete is just dots. So this is discontinuous. What is this one? This is our discrete. It is just dots, so this shows us discrete. Okay? So on the homework, on homework 1, it just has you say whether it is continuous or discrete. If it is discontinuous, just don't circle either one. Okay? So I'm going to put up that page. So homework 1, that's this guy, I have scheduled to be turned in on Wednesday. That is because I wanted to give you guys a chance, now that we know all these words, to look at them and try them. And if we have questions, ask tomorrow. Then we can turn them in on Wednesday. So I've got a little extra day for us. Yes, dear. Yeah. If anybody need a copy of this. Yeah. Okay. Oh, yeah. This is the one where you're like, oh, we're running really out of time. All right. I'm just gonna pass them out because I'm pretty sure like almost nobody picked it up. Oh my god, which is valid. Okay. If you already have one, either give it back to me or all right. So you guys have about 3 minutes left in the period. So give them a shot. See what you got. Let me know if I can help. Go from there. And then we'll keep looking at stuff tomorrow.